All right. Good evening. Good evening. Good evening. All right, does it work? Looks like the mic doesn't work properly. Good evening. Welcome to COM 9021. So where do we start? Maybe the course website, right? So you should have received an invitation to join ED. About 200 still haven't accepted the invitation, so please do it, because you won't be able to do much without access to ED. So once in ED, first you bookmark the page, right? Let's add this bookmark as favorite. Let's show. There we go. Right, so you don't have to look it up for it again and again. So what do we have in ED? First, a message board for you to ask questions and answer questions. Then we have resources with all kinds of resources to download. Then we have workspaces where you find, again, lecture notes in two forms. We'll talk about it a bit more. So to use these notes, you have to click on the fork button to create your own workspace and be able to work on these resources. Challenges, that's for practice exercises. Assessments, that will be for quizzes and assignments. And finally, lessons, that's just a few videos to explain to you how to install some software we need and do the first steps in using these tools, and also give you a bit of background on Unix. So that's actually all we need to work. So you don't need to install anything if you are keen to just work in ED. You can practice in ED, you can write programs in ED. You will all have to submit your work in ED, right? So you don't need anything else. Having said that, I guess that most of you will like to work offline. And of course, it's going to be a good idea to install Python and Jupyter, which is the two resources we need, we use in this course. So you can install both at the same time using Anaconda. So if you just do Google search, Anaconda, well, we don't want to go bushwalking, I guess. But the second link is the one we are after. So it is essentially Python plus a number of utilities, all packaged, nicely put together, and you can download it for your particular operating system, right? That's one way. If you want to have more control over what you install, you would have to install separately Python itself. So again, you go to the Python website, download. We use Python 3.8. Again, download for your operating system. And Jupyter also has its own website with instructions on how to install it, right? So Python and Jupyter. So I'm going to explain, of course, how to use Jupyter. We'll use it a lot. So now back to the reason why you happen to be here tonight, to learn some stuff. So what do we want to learn? First, we want to learn Python syntax. So essentially, vocabulary and grammar, right? Then we want to learn how to write well in Python. All right, so what we write with good style. How do you write a financial report? How do we write a tragedy? Even if we know vocabulary and grammar, right? There's of course much more to learn to do that well. And then we want to learn how to solve problems, right? Because after all, a programming language is nothing but a tool to solve problems. And how do we learn to solve problems? Well, obviously, by solving problems, all right? So we're going to learn all of that at the same time, right? So the approach is a bit unconventional. We're not going to separate that. We're going to say, here's an interesting problem. Let's understand it. Let's solve it incrementally. And as we go, we are going to introduce all the syntax, all the techniques we need to solve this particular problem, right? And eventually, we'll have come across a broad range of techniques and tools. We'll be very competent. It doesn't mean that you should not read a textbook, right? So particular textbook, for instance, will have a whole chapter on lists, which is just sequence of data, right? So we'll have 30 pages that will tell you everything about lists. Okay, so how do you find a particular element in a list? How do you change an element? How do you extend your list? How to remove elements from a list, right? That will be one chapter. So here, when we need a list, we introduce the concept. And then if we need to access an element, we explain how to do that, right? And that might be all we need for the first problem. Maybe in 2 weeks from now, we'll need lists again, but to do something else with the lists. We need to remove elements, so then we'll explain how to remove elements, right? So it's not presented by topic, right? It comes as needed. Okay? So you don't need to read textbooks. You can very well learn everything just reading the lecture notes, right? So the lectures are essentially here to help you approach the lecture notes, right? But you should spend time reading them. If you don't want to, that's fine. You can read a textbook, follow the more standard approach. It's good anyway. I think it's good to see something from different angles. Having different approaches to a particular field is always good. I still give you something close to a textbook in the form of Jupyter notebook sheets. So it's called references. So you can download it from resources, or you can directly play with that under workspaces. Reference. So let me fork it to create my own private resource. And here you see you have a number of topics which you can explore as you go. For instance, list and tuples. That tells you essentially everything about lists. So it's a very dense textbook, if you like, right? No bullshit textbook. And usually, you should be able to understand how things work. The good thing with this notebook is that you can test your understanding by guessing and then checking. It's a very good way to learn, right? So if you look at this cell, we defined a list, L, with a number of integers, right? What does it mean? We are asking if 0 is not in L. What is the answer? It is true, okay? Here we are asking if 5 is in L. What is the answer? Yes. So we can put the cursor in the cell, press Control, return, and so in this kind of cells, we have more than 2 outputs. So we can either run the first cell or do what's explained here, not to have to do that every time. That's just a technical detail, right? So you see, you guess and you check. Another one, L defined as this list. Len of L, does it make sense? If not, you see, above that there is a cell that gives you the documentation for the len function. Len question mark means, if I press return, okay, what is the documentation for len? And you see it gives you the number of elements in the container. List contains stuff, right? So we understand now what len happens to be. We can close this. What is the length of this list? 1, 2, 3, 4, 5, 6, 7 elements. So I guess Control return gives us 7, right? Now you can, of course, edit these resources, right? So we can here you can enter text, you see, when you are in Markdown mode. Right, and you can also introduce code, right? So if you wonder what is the length of the empty list, here we go, right? So we can adapt these resources to your needs, right? So a very good way to learn. Okay, as another example, let me just get rid of this. There's a particular sheet on control flow. We'll see that programming is essentially about doing things again and again, looping, and taking decisions, right? And most textbooks will have one chapter on loops, 30, 40, 50 pages. Okay. Computer science books tend to be awfully thick for no reason. One whole chapter on tests, 30, 40, 60 pages, right? Actually, it's all there, right? So you have two kinds of loops, for and while. Then tests, you are asking if something happens to be true, and then you can say if something else is true, elif. Else, if everything else was false, you can have break, continue statements. That's all. And I guess this particular cell summarizes that very well. And if you practice that, it gives you some output which changes because we generate random numbers, right? So this particular notebook sheet should help you without difficulty to understand everything about loops and tests, right? So there's something that is available to you. You use it or not. I'm just explaining it's essentially the heart of the textbook, right, with no frills. But again, this is optional. These resources, it's up to you to use them or not. All right? Another specific approach that we'll follow is to write from the very beginning the best possible code. Right? We have to be careful not to learn things the wrong way, because then it's very hard to unlearn and not the right way. It's also very hard not to be a powerful user. Right? If you think of how you use an editor, you might be a power user, but you might also, when you have to replace a word by another word, look for every occurrence of the word you want to change and do it one by one. Very inefficient, right? I type just 2 fingers, which is not good, but there's no way I will unlearn and learn to use all my fingers, right? So there is a big risk actually to start learning programming and feel we know programming, because indeed we can do stuff, but we do that in a very awkward way, right? We don't do that in the best possible way. So to avoid that, so I guess if you're a beginner, that's easier. If you know Python already, you might have to unlearn. So what I do is really to show you the professional way from day one. That means there is no notion of this is easy. We do that this way for 1 week, 2 weeks, 6 weeks, 2 months, 2 years. And later, we look at advanced features and we say we can do that better. No. In the first problem, we'll make use of features which are considered to be advanced, generator functions, for instance, generator expressions, that you wouldn't find in introductory courses, that maybe even experienced programmers wouldn't use, but that's the right way to use it. And there's actually there's good reasons why they show up for the first problem, because we should use them all the time. So we use that from the beginning, right? So there's no notion of easy, hard. We really learn the best practices from the beginning. So it might be a bit disconcerting, but I think it should pay off. So you're going to learn by reading and by practicing very regularly, right? You should practice every day. That's the best way to make progress in programming. So, of course, you will practice by playing with these Jupyter notebook sheets, right? By guessing and checking that your understanding is correct. That's one way to practice. Another way will be by, of course, doing the quizzes and assignments. And then another way will be to do the optional non-assessed assessments. Right? So you see in Ed, you have some part that describes the problem. Then you have a stub, so some Python code that you can run. So he does nothing. Edit it, run it, and get the output. And you can mark, that means check whether your output matches the expected output. Well, it wasn't at all about saying hi, but about doing something with the list. So of course you fail. And here you see the difference between your output and what I expect. But so you see, everything can happen in Ed, and eventually, when your code is correct, then the diff exits silently, and you get a nice feedback, well done, whatever. Okay? If you want also to practice offline, so you have different ways. First, you can download all these resources by themselves from resources, of course. So here they are. It's practice 1, 2, 3, 4, etc. Plus a few more, because there are a few challenges, a few exercises that I can't assess in Ed. So there will be a bit more there. So they are available as Python programs and also as Jupyter notebook sheets. So let me show you. Once you have installed Jupyter, you can, from the command line, execute Jupyter notebook. and that will give you access to all these Jupyter Notebook sheets, which I provide you with. In particular, those for the practice exercises. Now, to do things in a nice way, you have to do some preliminary initialization, right? So, depending on whether you're a Mac user or a Linux user, you have to use one of these files. So that's tested because I'm a Mac user. That's tested too because that's the school machines. That's not tested, so that's more of a guess. You will tell me if it works or not, and you will help me fix it otherwise. So what we have to do is to execute all these cells once and for all. So you see, in Jupyter, if you execute the cell once, you get here number 1. If you do it again, number 2. If you do another cell, number 3, right? And which is convenient because then you can retrieve previous commands. But here we need everything to be executed from 1 up to 6 with nothing before. So the best way to do this initialization is to click on kernel, restart, and run all. And everything is executed. And we should be done. Now, if we want to play with this particular exercise, so it will always be the same structure, things that import what we just created before. Here we say that we want to run every test for just 1 second, and we don't want to have more than that many bytes of output. Right, so this particular problem starts with actually a sample program that I asked you to study, and then describe what I expect from you. And here we'll run a few tests, and I'll check whether your tests, you pass these tests. So I could also write everything all at once. That's the sample program that asked me for a number. And since I run all the cells all at once, eventually you see I've run all the tests I created, and it turns out that I passed them all. So this is what the program asks you to do. Then you provide some input. Okay, so you see that what you provide as input is in blue. In case was something wrong, so in case the correct answer was not 96 but 95, you see you will get a diff that shows you the difference between what the output should be and what your output is. Okay, so that's another way also for you to learn and test your programs. Right, so many ways to work, either just in ed or locally. And that's a very nice way for you to test your programs. So in terms of homework, we'll have 8 quizzes. So before the end of the Wednesday lecture, right, I discuss the quiz for the week. So it's supposed to cover what we just discussed during the week, so you can practice that. And you have 1 week, so till noon of the following Wednesday, to submit your work, and you submit it by just uploading your file in ed, in case you work remotely. And whenever you press the mark button, I showed you before, there's a mark button that actually submits your file. So there's nothing else to do, right? So usually you press the mark button to check that you pass the sample tests. Of course, I'm going to use different tests, right? We'll talk about testing, of course, in this course. All right, so regular work with quizzes, and then 2 assignments. 1 assignment due in week 5 and 1 in week 10, I think. It's all described in the course outline, which of course you can also download from resources. So work regularly, then eventually we have a final exam, which is just practical exam where you have to go to the labs and solve some small problems, exercises. But you won't have to prepare for the final exam, right? I'm just checking that during this session you have acquired the skills step by step, and eventually you know how to do stuff well enough, right? So it's not a matter of preparing for the final exam, it's a matter of regularly, day by day, building this castle we want to build, and brick by brick, right? Day by day, and get there. And of course, my aim is not to make you Python experts, it's just to give you the right momentum, because it's not going to stop, right? What does it mean to know Python? It's not very clear, right? We can say that we know Python after Wednesday, because we will have seen already 80% maybe of the core of Python. Of course, Python is much richer than what we can cover in one course. First, you have the heart of the language, which is already pretty big. Then you have what is called the standard library, which is essentially extra syntax. That's already pretty big. If we go to the Python website, documentation, and then library reference. Here we see all the so-called modules that define syntax for specific purposes. And we'll see some of that. We'll see RE, we'll see what else? Math a bit, fractions, random, idle tools, func tools, but still not everything of those modules, and far from the 200 or so modules there, right? So that makes Python a huge language, and it's still not everything. Because if you go there, PyPy, you see more than 200,000 projects that have enriched Python with very useful syntax. For instance, if you want to scrape the web, well, you have a nice module. For instance, Beautiful Soup, sorry for the stupid name, to do that nicely. If you want to work with spreadsheets, you have another module. If you want to work with images, you have the Python imaging library, and on, right? Of course, you can't learn everything, but these are the tools we should need when we work on the relevant problem, right? So we keep learning, essentially, right? It doesn't make sense to say we know Python, we know some Python, and we keep learning more and more, right? So the aim of this course is not to tell you, that's it, you know Python. Not at all. It's to put you on track, give you some momentum, and make sure that you will keep working, you will keep practicing, right? Keep learning. And yeah, very important, of course, you come here to get support. So we also have consultation, right? So you can go to consultation for two reasons. One reason is that you are stuck on a quiz and assignment. I guess that's the main reason why you go to consultation, which is fine. But you can also go there to get feedback on your work. Because, you know, there are too many to get individual feedback. But you are encouraged to get feedback. So after a quiz, after an assignment, or for any of the sample programs, you are more than welcome to go to consultation, ask a tutor, can you tell me what's good, what's not so good about my program? How can I make it better? Okay, what is not optimal? What can be improved? And the tutor will be happy to let you know, right? And you can go consultation as many times a week as you like. We have 3 consultations now. No, 2, sorry, but we can have more, right? Also, as you know, because of the coronavirus crisis, not everyone is here, so we also have students stuck in China, and we provide online consultation to help them, hoping they will be able to join us before the exams take place, but nobody knows. Right? But anyway, we are here to help you, to support you, so by all means, get support. Any question on the admin side of things? So, okay, so good. So Jupyter is not really an IDE, right? So an IDE, integrated development environment, essentially a very powerful editor, right? Where you can write code in a nice way, test it, optimize it. And when you install Python, it comes with an editor called idle, which is not fantastic, but for small programs, it does the work, right? So by installing Python, you also install an editor which can hardly be called an IDE, even though it's called this way. You can still debug with it, put breakpoints, and it's okay, but not great. You have other IDEs, in particular Spider, PyCharm, and heaps of others, right? So on the school machines, for the final exam, you will essentially have either idle or Spider. That's pretty much it. You won't have PyCharm, okay? So it's good to be, but again, you don't have much to do in exams. You just have to write a few lines of code to solve question 1, a few lines of code to solve question 2, so you don't need power for that, right? But of course, locally, you're welcome to use any IDE you like, and if you use one already, then don't change. By the way, who knows Python at this stage? Who knows Python? Who doesn't know Python? So and there's a third group who might know Python or knows on Wednesday and not on Thursday. Okay. Everyone. Anyway, there's plenty of stuff, right? So there's much more material than what you can master if you're a beginner, right? So the aim of this course is to make everyone happy. So beginners will focus more on the core of the lessons, on the quizzes, on the assignments. If you know everything already, there's plenty of material there for you to study and become better, right? But when it comes to passing the course, really the expectations are not high, right? So my aim is to push you as much as I can, but have reasonable expectations when it comes to final exam. Right, so to get back to your question, sorry, Jupyter is not really an IDE, but something that's used a lot in industry, right? Data science, the whole data science community uses Jupyter. So, because it allows you to integrate, you have hardly seen it, but text, equations, code you can run, right? So it's a nice way to put all of that together. So for the lecture notes, same thing. So maybe I should say a bit more. Or if I go back there, notes, which you can access, of course, from downloads or from workspaces, as I explained. So I produce PDFs from these notes. So essentially, okay, something wrong. Let me try something else. Can you switch off your phone, please? All right, so PDFs, which is essentially all these sheets with all cells being run already. All right, so nice way for you to study. And at the same time, the Jupyter Notebook sheet itself, with again a mixture of, you see, text and cells, so that again you can practice as you go. You can, as explained before, guess and test, right? So 2 ways for you to work with lecture notes. One more passive and one more active. So you see, it's not really an IDE, right? It's more a nice integrated way to put together text, pictures, videos, mathematical equations, and code you can execute.
On the resources page where it says Notes 1 Turing Machines and Notes 2 the Monty Hall,
yeah.
Does Notes 1 refer to Lecture 1?
No, no, so that's a good question, because they're all unrelated. All these problems are independent. On the other hand, as I said, I introduce things gradually, step by step. So in notes number 2, I'm going possibly to be use some of the constructs, syntax introduced in notes number 1, plus introduce some extra. I explain the new syntax for notes 2, and I don't explain again the syntax we have seen already for notes 1, right? So from this point of view, it's independent, but the syntax is introduced following this particular sequence of notes.
So to prepare for a lecture, should I go through notes 1 or notes 2?
Notes 1, yeah.
Okay.
You start with notes 1. And okay, these problems, they are various complexity. Sometimes we spend very little time with the problem itself and just go straight into the code. Sometimes, in particular for Turing machines, we spend lots of time. The whole lecture today will be devoted on the problem itself. And we start Python code actually next on Wednesday, right? So it depends. But yeah, you're still, for that reason, expected to read them gradually, right? Any other question? Anything else? Yes?
So for the exams, you said that we have only the practical exams and no written theory.
That's right. Yeah, just practical.
And apart from that, as I'm new to Python, so like, what do you suggest me? Like, how do I start about it? Like, it's rocket science for me as of now.
Yeah, well, you try to follow what I say, and then calmly read the notes, read the textbook as well, practice, so do the practice exercises to the best you can, go to every consultation, do a bit every day, it will happen.
And the entire POP, this subject, will be about Python only.
That's right, yes.
Because I read on the Moodle about C or C++.
No. Python is all more than enough to keep us busy.
All right, thank you.
All right, so let's start with the first problem, Turing machines. So Turing machines are models of computers. So what do computers do? Difficult question. What do computers do? Exactly, I expected doing something simpler. They compute, they calculate, compute, that's the same, right? Indeed, computers calculate, they compute. Now, what does it mean? What does it mean to compute? Okay, so you have input, output, but is that the heart of computation? Is that what matters when we say to compute?
Perform operations.
That's very good. Indeed, we perform operations. Let's try to be a bit more precise. We perform in sequence and deterministically mechanical operations. So I think that's what matters, is the word deterministic. So at any point, there's only one thing we can do, right? And what we can do is mechanical in some way, right? So of course, that's still a very rough and vague definition. So the aim is to make that as precise as we can, and Turing machines give us a model to make that extremely precise. And then you will see why the answer is so interesting. So as you know, computers have a memory, right? So of course, we need a finite world. So memory is finite. But since Turing machines are a model, they are ideal in many ways. And in particular, we assume that we have infinite memory in the form of a tape. So you will see my great drawing skills. Right, so a tape infinite at both ends, consisting of cells, right? And every cell can contain either 0 or 1. So normally it's all zeros, right? But we'll have some cells with 1s, right? And of course, these zeros and 1s are meant to encode data, encode input, numbers, music, videos, text, whatever, thanks to a particular encoding schema. So here we just encode positive integers, right? So as you probably know as well, computers encode integers using base 2, right? So 0, 1, 2, 3, 4, 5, 6, 7. So that's written in base 10. In base 2, that's represented as 0, 1, 2, 3, 4, 5, 6, 7, right? Read about base 2 if not too clear how it works. Anyway, here we'll do things in a much simpler way. We'll use base 1. We'll use unary notation. So base 1, we can't encode 0, essentially. So we don't play with 0, but we'll play with 1 as 1 bit set to 1, 2, 3, 4, 5, 6, and 7. That's how we encode these numbers. Okay? So you see here our tape encodes, contains, if you like, the number 3, right? That's for the memory part. Now we are going to look at the Turing machine, just looks at one cell. It's a big difference with, so by the way, yes, I should have said before, Turing machines are very interesting, and in particular, we are going to learn our first programming language. Right? So as we program Turing machines, we can really think that we learn a particular programming language, that of Turing machines, and we also learn how to program by thinking in a particular way. Right? So it's very useful work. It's not just theory. We are really working to become computer scientists and think as computer scientists or engineers. Right. So you see, if you have, let's say, a picture of a cat, I guess you step back, you see the whole picture, and you say, well, of course it's a cat, right? But computers don't see the big picture. Right? Computers see only very locally. So with a picture, they would see one pixel, right? They will be able to say this pixel is red, and it has that luminance, right? And that's all I see. So to know what the picture is about, I need to explore my picture. Maybe I should go to the right. What's the picture on the right? Is it the same color? Is it brighter or darker, right? And move in a smart way. Remember things in a smart way, but you can't remember everything. And eventually, based on my exploration of all these pixels, I think it's a cat, right? So that's a big difference, and that's very important to understand, to think like a computer. So it means we look at one cell, and when we start, we are going to look at the leftmost one, right? So the beginning of our input. And then we'll have a number of instructions, and at most one instruction will apply depending on what we see and which state we are. Okay, so first, when we look at a particular cell, we'll see either 1 or 0, right? Then we have the choice between, if we see 1, keeping this 1, or changing it to 0. If we see a 0, we have the choice between leave 0 as it is, or change it to 1. So first, we can do something to what we look at. And then we'll have to move either right or left. Okay, by one cell only. We have to move. And of course, we have the choice to do this. I mean, if that's all we could do, then our Turing machines wouldn't be very powerful, right? So we have to say, in case I see a 1, in this state, in this mood, I keep it. But in case I see a 1 in that mood, in that state, I change it to 0. Right? So we have a number of states that tell us what to do seeing this. And as we do this, meaning change this bit or keep it, move right or left, also let's either stay in the same state or change state. All right? So you can think of the state as a memory of the past. If we had infinitely many states, we could remember everything. We could remember that we started seeing a 1, we kept this 1, we moved to the right, that was a 1, we kept it, moved to the right, that was a 1, we changed it to 0, and here we are. Right? So we could remember the whole past. But we don't have this luxury, so we just have to remember enough of the past to, okay, what matters, what has happened which matters, and that should be enough to let us know what to do. Okay? So instructions of the Turing machines will be of the form: if I am in this state and I see this bit, either 0 or 1, then my state becomes state prime, possibly state itself. It might not change, right? This bit of 0, 1, I keep it or change it, and then I move right or left. Right, so quintuples. In this state, seeing this bit, I do this to this bit, I do that to my state, and I move right or left. Okay, so let's start playing by writing our first program. So we first have to know what we want to compute. I suggest computing the successor function. Imagine you have a pocket calculator, you input 13, and you want to press a special key that prints out 14. Not the most useful key, but we have to start, right? Successor function. That means if our Turing machine contains the input 4, that means we have 4 consecutive ones on our tape, and we look at, to start with, leftmost 1. We have to eventually stop with 5 ones, 5 consecutive ones on the tape, right? Plus, to make sure that things look clean, things are clean enough, we want to, when we stop, to have the head position under the leftmost one of the output, right? So we don't allow 0 as input. So input can be only 1, 2, 3, etc. Output can be 0, in which case the tape is nothing but zeros and the head is anywhere, right? Or the output is not 0, so some ones, and we want to look at the leftmost one. Okay? So first we have to solve this problem. So what is the idea? What do you think? So first we look at things at a high level. We don't need to know about English. We don't want to solve things in terms of instructions, not yet. The first step is to solve the problem at a higher level. So have the high level idea. So what do you suggest to do? Of course, we could erase all these ones, right, and output and write 5 ones very far to the right or very far to the left. We can do anything we like, but what is simplest? What is a simple approach?
Take 1 step to the left and change it to 1.
That's right, but that's too smart. Another idea, we'll go there. Another idea, usually, people are not that smart, okay? They think, well, let's just go all the way to the end, okay? And then, after we have seen all ones, we'll find the 0, and we'll change this 0 to a 1, and then we'll move back to the left, right? So eventually, we're going to see the first 0 to the left of our input, now output, and then move 1 step to the right. Okay? That's one possibility. Okay, so let me go to the end, find the first 0, change that to a 1. Now I have the number of ones I want, and to have a clean configuration. I just go back to the beginning. So we start in what we call the initial state. Let's call that the grumpy state. Right, so we are grumpy, and we see this one, right? So which instruction do we need to go all the way to the end and see the first zero? This one, what do we do? Do we keep it, or do we erase it and change it by 0? We keep it, right? We don't want to erase this one, so we keep it. Then, are you going to move right or left? Of course, right? We want to go all the way to the end. And should our state change? Essentially, grumpy state is the state where we keep reading the input, right? So we remain grumpy. Right? So when we start, we ask, is there? So we start in grumpy state. That's the initial state. We see a 1, and we ask, does our Turing machine have an instruction we can apply? Yes. And it has only one instruction. It's deterministic, right? Being grumpy, seeing a 1, there could be no instruction or exactly one instruction. There is exactly one. Tells us, go there, staying grumpy, go there, staying grumpy, go there, staying grumpy, right? And eventually, go there, right? So eventually, in the grumpy state, we see a 0. Right? Make sense? What should we do with this 0? We want to change it to 1. Do we want to move right or left? We want to go to the beginning now, right? So we want to move left. And should we remain grumpy or not? What happens if we remain grumpy? If we remain grumpy, let's say we have 2 as input. I look here, right? I'm grumpy. I go to the right. I move here. I'm grumpy. I go to the right. I move here. I see 0. I change to 1. I say I move to the left. If I remain grumpy, what would happen? I move to the right. I move to the right. I will see the 0. Change it to 1. Move to the left. Being grumpy, move to the right. Move to the right. See 0. Change it to 1. You see, I would forever add more and more 1s, right? But what I want, of course. So I should not be grumpy, and indeed, that's now something else, a new stage in this solution, which is now starting. So I can be glad to have found the zeros to the right, and now I gladly go back to the beginning, right? So in a glad state, when I see a 1, what do? I go to the left for sure. The 1, do I keep it? Of course, I don't want to waste anything. Do I change my state? No. I remain glad. At some point, being glad, I will see the rightmost 0 before the sequence of 1s, right? So since I want to finish under this 1, what do I have to do? Being glad, seeing a 0, I just have to go to the right. I don't want to change this 0, right? That's fine. And I change to a new state, let's say done. And now I will be looking at this 1 in the state done, and I see I have no instruction that tells me what to do in state done, single 1. So I stop. Okay? So we have a widget. So It might be a bit small in terms of content. Sorry for that. We can play with this widget where you have a user manual that explains to you how to play with widget. So I can control click to the right or to the left to add cells. If I control click again, the rightmost or leftmost cell, I just delete it. And then I can simply click to change ones to zeros or zeros to ones, right? So now I've got a tape that represents the number 1, 2, 3, 4, right? Let me quickly write the program we designed. So being grumpy, seeing a 1, I remain grumpy. I keep the 1 and I move to the right, okay? Eventually, being grumpy, I see a 0, which I change to a 1. I will move to the left in a glad state. And being glad, seeing a 1, I stay glad, keep the 1 all the way to the left until I see a 0, where I move to the down state, keep my 0, and move to the right. Okay? That's exactly what we wrote before. Now we can start. What is the initial state? It is grumpy, right? And we see that the head is represented here by making this cell red, right? So I'm here looking at this one in the grumpy state. So this particular instruction applies. So next step moves me there, moves me there, moves me there, always grumpy. Get there. Now seeing this 0, right? Grumpy, seeing 0. I change 0 to 1. I move to the left, and I become glad. There we are. And then we move all the way to the left until we reach this 0. Seeing this 0 in the glad state. We change the state to done. Keep the 0, move to the right, and that's it. And in 10 steps, we have computed the successor of 4. Make sense? What is the complexity of this program? So the complexity is a function of the size of the input, right? Not the value, but the size. So if my input has a size x of 5, because I have encoded number 5 this way, how many steps do I perform to eventually stop? 10, maybe plus 2, right? Because before we had our widget shows that we computed the successor of 4, and there were 10 steps, because we go one step beyond to the right, to the left, right? So we need to add 2. So the function, the complexity function, S of S is 2S plus 2, right? I don't really care about plus 2. But so it is linear, right? Again, linear in the size of the program. Of course, if we worked in base 2, right, so 5 would be presented as 1, 0, 1, and S, okay, so S would be 3, wouldn't be 5, right? So the size would be the log 2 of our input, or rather the ceiling, right? So the largest number the smallest integer at least equal to the log 2 of a number. Anyway, let's not get too distracted. Complexity of this program is linear. Most programs have a complexity which is at least linear, just because you need to see the input to do something with it, right? So you need at least to read the input. That makes your program at least linear. But here indeed we had, if we scratch our head or not, we think we don't need to do that, right? Why do we go all the way to the right? We can just add this 1, not to the right, but to the left. So what will be the program? Being grumpy, seeing a 1. What do I do? Same thing, except that I remain grumpy, but not for long. Because I go to the left, and then I'm sure to see a 0, right? And now, grumpy space, state, seeing a 0. I need to change the 0 to a 1, change to glad, and turn to go right or left. Well, we can't really stop, right, if we want to be clean. So if I have 1, 2, 3, right, I'm grumpy, seeing this 1, I move to the left, I see this 0, I change it to 1, I change to glad. I have the choice between going either here or there. I have to move. All right, so 1 step to the right or 1 step to the left. So it doesn't matter. If I go left, then I have to go right. If I go right, I don't have to go left. So it doesn't matter. So let's say if I go right, then in a glad state, seeing a 1, I will change to done, keep my 1, and go to the left. Right? So let's check. All right, so the input is 4. Start in the grumpy state. What happens? We go there, change the 0 to 1, and remain grumpy, right? Now we are grumpy, we see 0, we change it to 1, and go to the right, so here, becoming glad. And now, being glad, we see a 1, we go to the left, keeping this 1, and change the state to done. And we have no instruction for the done state, so we are done indeed. How many instructions? 3. Complexity, constant. It doesn't matter if your input is 4, 5, 2 million, right? It's constant. So it's one of these rare programs where we don't need to read the input, right? We don't need to know what the input is to do the job. All right, so here we had this great solution to start with, but very often you will see that we come up with a solution which is maybe not optimal. And then you should not say, okay, I get the output, I'm done. You should ask yourself, can I do it better? Can I improve it? Can I make it more general, more efficient, more elegant? And most of the time the answer is yes, right? If you have a look at, for instance, in mathematics, if you have a look at the proofs of the great results we know today, they have been simplified and simplified and simplified, right, as people think about it. We don't go straight to the simple solution. So if you really want to become a good programmer, you should have this discipline of always asking yourself, can I make it better? And often the answer is yes. And if you can make it better, right? So don't bother if you spend 10 hours for this solution thinking, well, spend 10 hours, that's good. No, take the time to just do it the better way you thought about. It's not time wasted at all. It's good time well spent. Okay? So that was our program for successor. Now let's think of something more interesting, not fantastic, but useful for sure, addition. So if you want to compute 4 plus 6, so our input will be 4 and 6. Now we have two numbers. So how do we present our input? What is natural? Well, we can just have 1, 2, 3, 4, first number, then have a separator of 0, right? And then second number, 1, 2, 3, 4, 5, 6. Right? It's a natural way to represent the input as two numbers. And as always, when we start, we'll be in the initial state looking at the leftmost one of the first input. Okay? So now we have 4 ones and 6 ones on both sides of a separating 0. And eventually we want to get 10 consecutive ones. Let's solve it. Again, not thinking low level, but high level. So what is the key idea? I guess we should probably glue these two things, right? So instead of shifting, for instance, what's on the right to the left, why not? It's probably not optimal, right? So something simpler would be, well, we want to glue these things. The issue is this 0 in between. Let's just change this 0 to 1, right? If we change this to 1, then we are done, except that we have one extra 1. So we should remove a 1. And again, we have the choice between first and last. And based on our experience with the first problem, probably prefer the first option, right? So let's delete the leading 1 of the first input. And then let's move to the right and see the separating 0, which we replace by 1. And then we just have to go all the way to the left to nicely align the head with the leftmost 1. Okay? So now we have two numbers, m and n. What is the complexity of this algorithm? Is it constant? Is it exponential? Of course not. It is? No, because you see, if your first number is very large, you need to, find the. So it's. No, there's no log here. Yeah, exactly, yes. So 2n plus 1, it is linear in n. It is linear in the size of the first input, right? In other words, the second input doesn't matter. You don't care. But the first input does matter, right? So linear in m, which is, of course, great if m is small, and all the more great, or the greater than n is large. Okay? So, let's start with state Q0. Okay, I don't want to write. I'm afraid you can't really see well at the back, but in state Q0, we see a 1, starting with the leftmost one of the first input. What do? We remain in state Q0, we keep our 1, and we move to the right. Okay, so we keep, or we could, instead of Q0, right, move right, M-O-V-R. Right, so the idea is I move to the right. And the name of my state expresses it. Right? So eventually, instead move right, I will see the first 0, the separating 0. No, we don't do what we say we should do. We said we have to change the first 0, the first 1 to 0. And move to the right. Should we stay in the same state? If we stay in the same state, we're going to erase the whole of M, right? Okay, so let's say we start in the state del for delete, and we change to state move right. Okay, so I see in the del state the first leftmost one, I delete it, change it to 0, move to the right, and change my state to move right. And now, in the state move right, for as long as I see 1, stay in state move right, keep my 1, and go to the right. Until in state move right, I see a 0, which I change to 1, and I change my state to move left, M-O-V-L. And indeed, for as long as in state move left, I see a 1, I stay in this state move left, I keep my 1, move to the left, and that will take me to the 0, just input. So in state move left, when I see a 0, I keep my 0, I move right, and I'm done, right? So let's check it. Three, 4, separator, 1, 2, 3, right? So 4 plus 3, we want to get 7, okay? We start in state del. In state del, seeing a 1, we delete, we change our state to move right, and stay in this state until we find the 0 in between. This 0 in state move right is changed to 1. The state is changed to move left. And we go to the left and keep going to the left in the same state until you find the 0 before, at which point we move to the right and change the state to done. So now we have 1, 2, 3, 4, 5, 6, 7. Okay? Got it? So something a bit trickier, so that keep practicing. So you see, this is a programming language, right? Now you will, before we look at before we look at the next example, you might think, this is too simple, right? For sure, Python is more powerful. Right? Is that what you think? Do you think that this is too simple and Python is more powerful? If you think this way, you are wrong. Of course, Python will be more efficient. We won't do things this way. But everything we can do with Python or with any language, we can do it, of course, in a very awkward way, with Turing machines. That means we seem to understand it, and then we came up with other models of computation. So let's define compute in another way. And people came up with heaps of models of what it means to compute. And they have all been shown to be equivalent to this. So it looks like whichever way we look at it, to compute really means to do something like this, right? Now, Turing machines have a very nice property, namely, there is a universal Turing machine. What does it mean? It means I can give two inputs. One, which is the description of a Turing machine, of a program, a description of this, for instance. I can encode everything, right? I can encode numbers, pictures, music, whatever. So surely I can find a way to encode these instructions. It will be the first input, right? And then the second input could be the input I want to give to the machine I encode. And then let this special Turing machine simulate the first machine on that input. All right? That's a universal Turing machine. A Turing machine which simulates the workings of any Turing machine on any input by giving as input to this universal Turing machine an encoding of the coding machine to simulate and an encoding of the input on which the simulated machine should run. Why is that important in practice? What does it mean in practice? No, something much more important than that. If we didn't have a universal Turing machine, right, so it means for every particular problem, have no choice but build the Turing machine to solve this particular problem. Other problem, I need another Turing machine. So it means if you have a problem, if you want to write a program that scrapes the web, you would have to order Dell or Lenovo or Apple or whichever company a particular computer that can solve this particular problem. You have another problem, you have to again go to this company and buy a new computer. It would be great for them, but not so great for us, right, and for the environment. So really, these machines we work with are, of course, implementing a universal Turing machine. That means they simulate the working of every Turing machine, right? So they simulate the working of any solution to any problem, right? So see the deep, important consequence. So now let's look at another example. Division by 2. So we work with integers, right? So when we have a division which is not correct, I just want to discard the decimal part. So I want to compute 8 divided by 2 as 4, but also 9 divided by 2 as 4 as well, right? So in other words, I want to the function that gives me the floor of n divided by 2. Okay? So let's think. Let's say the input is 6. We want the output to be 3. How? Again, let's solve this at a high level. You move to the right all the way, or?
All the way,
So we go all the way to the right. But how do you count the steps? We only have these instructions. Any idea?
turn every second 1 into a 0.
Okay, so if you turn every second one into 0, then you have some Swiss cheese with plenty of holes, and you have to glue them. So maybe for that problem, it's better to have the output written somewhere else. Maybe you should say, for every 2 ones in the input, right? We want to process them, so we want to eliminate them, and correspondingly add a 1 to the output. No? There you go. Confirmed. So I see a 1, I delete, I move to the right, I see a 1, I delete, I move to the right. I've deleted 1, 2 ones. I know that now, having deleted 2 ones from the input, I should add 1 1 to the output. How to do that? Well, by first going over what remains of the input, if anything, right? Eventually, I'll see the separating 0, separating what remains of the input from what I have at the output, right? Move to the right, and now I am in output zone. I want to get to the end of this output. Well, when I start, there's no output at all, so I'm where I want to be. I can replace this 0 by 1. Now it's time to go back, right, to process what remains of the input. So go over all the ones of the output. Actually, there's nothing at this stage, so I immediately see the separating 0, right? Go to the left. If there's a 1, something left in the input. So go all the way to the left until I see the 0 that's just to the left of what remains of my input. Go to the right and do that again, right? So delete, go to the right, delete, go to the right, go to the end of my input, see the separating 0, go all the way to the end of the output, so we go there, here it is, change the 0 to a 1, and go to the left over the whole output, separating 0, the whole input, go to the right, erase, erase, go to the end, add 1. At this point, when I see the separating 0, I go to the left, I see a 0, so I know there's nothing left of the input. All right? Make sense? What happens if I have an odd number of ones, if the input is an odd number? I know I want to delete 2 ones, right? So I will be in state. For instance, if my input is just 1, I will start in state, let's delete the first one out of potentially 2. I go there, and I will move there in state del 2, which means let's delete the second one. If there is one, there is none. So it means I just had an odd number. This number minus 1 has been processed properly before, and I'm done. Many, well, no, it's not the only solution, but so you can think of other ways. But this is probably the simplest way. So to make sure everyone can read, maybe I don't write it with the widget, right? So I would start in state del 1. Okay? What do I do? Seeing leftmost one, what do I have to do? Change this one to 0, of course, move to the right, and change to state del 2. I have deleted 1, now I have to delete, if possible, the second one, right? So in state del 2, seeing a 1, I delete it. And I move to the right, and now I change to state, move to the right, processing the input, right? Move to the right input. So for as long as moving to the right in this state, I see a 1, I keep going, right? Eventually, in this state, I see the separating 0. I keep it, and I move, I change to state, move to the right, output. And for as long as there is something to go over, I go over until, instead move right, output, I see the 0, which is the first 0, to the right of my output. This 0 is changed to a 1. I'll move to the left. In state, move to the left, processing the output. All right? Lazy. That's exactly what we are writing, right? We're just there. Right? Except that I used 1 for input and 2 for output. That's all, right? So move in the first section, if you like, and move in the second section, right? And the rest should be clear, right? And you see that eventually we have processed either all ones, with the possible exception of the last one of an odd input, right? So in case our number, you see when we move to the left, right, over what's left of the input, if anything, that's the instructions, eventually we find a 0, right? We move to the right. What change do we change to? We are about now to start deleting the first one of a sequence of 2, if any. Right? So the crucial part, you see del 1 is the first state, the initial state, but it is also the state you get back to after you have deleted the first two ones, put it one in the output, came back, and found the first 0 to the left. Okay, then you go to the right. You should see if there is something left, the first one of what remains of the input, and that should be processed in state del 1, right? If in state del 1 you see a 0, it means the input was even, right? So you just need to go. This 0, of course, will be the separating when we see del 1, 0, right? Move to the right. So now we are seeing the separating 0 between the input, which is gone, and the output, right? So we just need to go to the right, keeping this 0, to be under the leftmost one of the output. Now, if our number was odd, in state del 1, we see a 1, we delete it, we go to the right, and now in state del 2, we see a 0, which is the separating 0, right? So again, you just need to go to the right and move to a state with no instruction. Make sense? So we won't practice more, even though we have a program for multiplication. So we can do three things essentially. First, just ignore. Why not? Second thing, just do it all the way, as we did here. Very good. What you can do, and what I advise you to do, is to go in between. So essentially, think of how to solve it, okay, at a high level. So think up to the point where you are convinced that now it's just a matter of translating your vision into code, into Turing machine instructions, right? It's just a formality. You know that somehow you have reached this stage precise enough in your mind. You could do it, right? And then run the simulation, run this widget, and see, by understanding how it behaves, whether it's exactly your idea, right? And in case it's not, compare both. That's very interesting to do. So let's start now learning Python, meaning capturing the essence of this widget, right? So we don't want to implement the widget, that's a bit too ambitious. But we want essentially to capture what is important in this widget, all right? So let's create a new sheet, Jupyter sheet, and start learning Python. So what do we need? We need first to represent the tape. Well, the widget, of course, doesn't make any assumption on how big the state could be. You can play with it. You can have a program that runs forever. It will run it for 1,000 steps. Stop, 1,000 steps again. You will have a hard time to crash it, right? Eventually, you might have a tape with billions of cells, right? So the widget is smart enough. We want to be less ambitious. We just want to represent just a finite section of the tape, large enough so we know what we want to simulate, so we know that we are going to try with this input. We know that what we want to simulate doesn't need to go beyond that many cells to the left, beyond that many cells to the right, right? That will be good enough. So we are going to use a Python list. So Python list is nothing but a way to represent a finite sequence of data. So if we want, what's going on So here we create a list meant to represent a cell where at some point we have 0, then 0, then 0, then 4 ones, then 0, then 0, then 0. Right? So a fraction of the tape that contains what we intend to be the input for with a bit of space at both ends. Right? So that's what we call a list literal. Right? So it's a particular concrete list. And L now here is a name that refers to this entity. So what happens is in memory, Python will encode these ones and zeros, right? We'll store there somewhere. And of course, we'll know where this representation starts, right? And L is just a name of where this presentation starts. So if you know C, it's not at all the kind of semantics of C where you say you allocate memory for L. It's not that. Okay, you should think of L as a label that you stick at this particular location of memory to say that's where it starts. Right? And now Jupyter lets me display L, or lets me print L, no difference, right? So with this line, I'm just evaluating L. Okay? I'm just finding what is the value of L and just outputting a representation of that value. And here I'm nicely printing this value. But it turns out in this case to be the same. It won't always be the same. So you see we can create lists this way. Of course, let's say if you wanted a list of 20 ones, that'd be fun to write between square brackets, 1 separated by commas 20 times. So we can, luckily, use the times operator that can have different meanings, depending on the context. So of course, if we apply times to the numbers 2 and 3, that means multiplication of numbers. Result is 6. But if we have a list L, which is set to 1, 1, 1, and we multiply L by 3, this way or that way, essentially, we're creating a new list, which is 3 times the list argument. Okay? What is this? 1, 2 times 0. The empty list. Okay? So a list with no copy of 1, 2. That's the empty list. Okay? What is 1? Why do I keep changing? It's too sensitive. What is this? That's the same list. And what is this? It is the list 1, 2, 1, 2, 1, 2, 1, 2. Okay? Yes.
Like, why is it like this? Because I know that in other languages, like, it's not like.
Yeah.
Why
Well,
is it Python?
yeah, so Python is polymorphic, right? So it gives meaning to these operators that depend on the types of the operators.
So they're overloaded operators by like that.
Not this notion, but something like that, yes. Shh. We'll understand better this later. Okay, so now if I want to have a list with, let's say, 2 zeros 20 ones and 2 zeros. What can I do? 20 ones that I know, right? To have 20 ones, I just do the singleton list 1 times 20, right? That's the simplest way to create a list. And then I need to add to that 0 at the beginning, 0 to the 1, right? So for that I can use another operator, plus, which of course, if you provide as arguments numbers, 10 plus 34 gives you 34. But in case you provide lists as arguments, glues them, right? Appends them. Okay? What happens if we add a list to a number to a list? What do we get? What could that mean? Nothing. Okay. So multiplication, Python could give minimal sense to that, but it doesn't give a sense to that, doesn't know how to add a list to a number, so it generates a particular kind of error, and it's a type error to say that the types of the arguments don't make me happy, right? They're not. So now tell me how to get 2 zeros, 20 ones, and 2 zeros. I guess 0, 0. Not worth to say 0 times 2, right? Let's not be pedantic. Then plus, then 1 times 20, plus 0, 0. Right? And you see, we have an operator, plus, used twice. It happens to be left associative, which means from the two lists 0, 0, 21s, we create a new list. And this new list is then merged, then gives us a new list with the second 0, 0. Right? Fine? So now I guess we are going to play with tape. As we know, the tape will change, right? We keep moving, changing stuff. It would be nice to be able to represent the tape. So to represent the tape, the widget does something nice, but we won't be so ambitious. So what I want, if I have my list L being equal to 0, 1, 1, 1, 0, 0, I want to be able to display this list as 0, vertical bar, 1, vertical bar, 1, vertical bar, 1, vertical bar, 0, plus 2 vertical bars at both ends, and then to represent the tape boundary, to have hyphens above and below the zeros and the ones and the vertical bars, like this. Right? And since I want to output this many times, I'm going to define a function, so not write just the code to do it and copy and paste this code whenever I need it, but I'm going to define a function display tape, which will take no argument. But I want to, and here I'm writing a comment. So I'm essentially writing the specification of my function. So what do I want this function to do? Display horizontal boundary, okay? Then display tape contents, and then display horizontal boundary again. Okay. So see, I'm defining a function, therefore define a function that in this case takes no input. We just do something. Return. Python is not happy because it wants the body of the function, what the function actually does, not to be empty. It has to be at least one instruction. So at this stage, I don't know what to do, so I can just use pass, a statement which means do nothing. And now Python is happy. It knows about this definition, about this function. Okay? Now you see, we want to do something twice, right? Display horizontal line, horizontal boundary, to start with and to end with, right? So instead of writing code to do that and copying and pasting to do it again, it is nicer to define another function, def display horizontal boundary, that display tape will use call twice. So what do I want to display? I want to display these hyphens. How many do I want to display?
2n plus 2.
Yeah, so if n is the number of elements in my list, 2n plus
2ln.
no, 2n plus, not plus 2, right? Because you have one hyphen to the left, which is the vertical bar, one hyphen for the element. So 2n, that gives you everything except for the vertical bar at the end, right? So probably more 2n plus 1. You agree? Where n indeed is the number of elements. So question, how do we know the number of elements of a list? Well, we actually saw that before, right? So if I make L equal to this, and if I'm asking what is the length of L, I get 20 plus 2 plus 2, 24, correct? So this function will print
You have to pass in the
24 times 2 plus 1. Okay, so what can I do? Well, maybe I want to create a sequence of hyphens, which is long enough. So we have seen numbers, list of numbers. We also have characters, right? So between single or double quotes, we can have text, right? So sequence of characters. So we would like to print out, to display such a string consisting of 24 times 2 plus 1 hyphens. Any idea, knowing how elegant Python happens to be? We have seen before we could use times to multiply a list by a number, right? What about multiplying a string by number? Nice, that works. Okay, that gives a new string consisting of the original